too, but I already read it.
All right, let's jump in. So, this class recording has started. So, on Wednesday, we began to talk about how the type of bond can affect the properties of the compound that makes up the compound. Sorry. The type of bond affects the properties of the compound. And we said that there is really one factor that determines the properties of that compound more so than everything else. And if you look in your outline from Friday, you might be able to, or Wednesday, sorry. If you look at your outline from Wednesday, you might be able to find it. It's right at the very, very beginning. What's the one factor that really goes a long way to determining the properties of this compound? You have to go back and look. Energy, yes. More so how much energy we have to put into something in order to do what?
Overcome attractive forces in particles.
Okay, so like the one thing that really determines this is the attractive forces between the particles. How strongly do those particles that make up this substance hold on to each other? The stronger they hold on to each other, the harder it is to separate them, or the more energy that we have to use to separate them. Good? So, Friday we talked about ionic solids. First, how are ionic solids arranged? How are they situated? Actually, let's go with this. Most ionic solids exist in what state of matter? Solid, right? That's why they're called ionic solids, right? Because they are very strongly attracted to each other, or the ions are very strongly attracted to each other. And we refer to that as what? The strong attraction between the ions that make up this ionic solid. Maybe at the very, very bottom of the first page. Liam, go ahead. Interionic forces, which, if you know English, should make sense to you, right? So, interionic forces are very strong. And because of that, that causes the property, or it causes ionic solids to have a specific property, or a couple of specific properties. What kind of properties do ionic solids have? You can look on the back of the first page. That might help you. Where it says properties of ionic solids, that might, general properties of ionic compounds, right? So, good.
High melting and boiling points.
High melting and boiling points, and that means that they're generally what state of matter? Solids, right? But, even because of that, we can see some differences. For example, here, these didn't come out as big as I wanted them to, but that's okay. Okay. Here is the melting point of sodium chloride, 1,474 degrees Fahrenheit. That's pretty hot. It means we got to heat that thing up. We had to heat that salt up pretty hot and turn it into a liquid. But if you look at barium oxide, 3,493 degrees Fahrenheit, almost twice as hot. Why? I had you draw a picture, or I had you actually figure out a formula on Friday, or Wednesday. I'm glad it's Friday today, because, so. What is the formula that I had you figure out on Wednesday? I figured out sodium chloride for you, but I had you figure out, I'll give you a clue, it's on board, barium oxide, right? And we said that the ratio of cations to anions in both of them is 1:1. But how come barium oxide's melting point is so much higher than sodium chloride's melting point? In barium oxide, how many electrons are we trading back and forth? Well, where's barium on the periodic table? 2, right? So it has 2 valence electrons. Oxygen is looking to gain 2 valence electrons. So, instead of sodium plus 1 holding on to chlorine minus 1, it's sodium or barium plus 2 holding on to oxygen minus 2. That's a stronger attraction. What's this?
Salt.
Well, say again? Could be NaCl, but if we did barium oxide, it would also look like this too. What did we call this in general? That is a crystal or a crystal lattice, right? Ions in an ionic solid are not only connected to one other ion, right? We have this three-dimensional interconnected network, right? And this means that the interionic forces are very strong because one cation isn't attracted to just one anion. It's attracted to a bunch of other anions, right? And that's also why we have that red, white, red, white, red, white alternating pattern. Okay? Good there? Okay. Forces of attraction, very strong, high melting points, properties of ionic solids. Good there? Okay. To bridge the gap, let's take a look at a molecular solid that is almost as strong as ionic solids. And that molecular solid that we're going to talk about is a diamond. I think most of you probably know that diamonds are really hard, yes, right? And also very strong, okay? Here is diamond, okay? So, first, what do you notice about the color of the circles that make up diamond? Black, right? And they're all black. Is diamond a compound? No, right? Diamond is an element. Okay? We know what element diamond is? It's carbon, right? So, just a bunch of carbons linked together. However, this is also carbon, all black. Okay? This is graphite. Okay? Everybody know what graphite is? Pencil lead. Okay? We can also use graphite as graphite sometimes as a lubricant in like industrial processes, like like PAM, like things slide back and forth and stuff like that. Okay? So here they are. I'm trying to hold them like this in a specific way. Okay? What's the difference between this and this? Right? Think this. Okay, they're more spread out, right? If you look, I'm trying to hold it in a way to make it obvious, all right? They're a different structure, definitely. Can we tell the difference between the structures? One's tighter. Which one's tighter? Diamond is tighter. Dustin, what else?
It looks like the one on that side has like 3 rows.
Ah, the one on this side, it's like 3 distinct rows, right? We see that? Are there any distinct rows here? Okay. We said that the stronger that things hold each other together, higher melting points, harder it is to change one state to another, etc., etc. These are high attractive forces. Here, the ones that are in the same row are attracted to each other, but is there a whole lot of attraction between rows? Not really, right? So that makes it much easier here just to sort of lop off the top row, right? And then we're left with these rows. Guess what happens as you write with your pencil? The top row comes off, right? So as we're writing across the paper, this row gets left on the paper, then this row gets left on the paper, then this row gets left on the paper, right? And we just keep going down, 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 down. Can you write with a diamond? I mean, you can scratch other things, I suppose, right? But this doesn't leave carbon atoms laying on the on the paper. Why? Because how connected are they? Really connected. Okay. Yeah, go ahead.
So you can't burn a diamond like it's coal?
No. Coal is carbon as well, though. But getting back to something Charlotte said a long time ago, right? Burning something is separating all these atoms and turning them into something different. It's a chemical reaction. We'll talk about that more in the next section, in the next unit. Okay? But in order to have something react with something else, you really need to separate all the atoms so they can react with other stuff. Basically what's happening in a chemical reaction is you're taking stuff that's in one state and bonding it to something else. But in order for it to bond to something else first, you got to separate it from what it's connected to originally. Does that make sense? Okay. Diamond doesn't burn like coal, even though they're both carbon, because they're so interconnected with one another, it's hard to separate them apart so they can react with something else. Does that make sense? Good, Trey.
So does diamond have a melting point?
Your diamond had a melting point. If only we could go somewhere and find the answers to these questions. So, I know this is Yahoo Answers, but so it's kind of weird. Oh, there it goes. So the melting point of diamond at surface pressure is around 3,550 degrees Celsius, okay? Which is Celsius. So that's even high. That's even higher than the melting point of barium oxide, which is 1,923 degrees Celsius, right? So that interconnectedness of those atoms makes it really hard to separate.
So is it around like 10,000?
3,500.
More like 12,000.
There you go. So,
I just like
there you go.
it.
Apparently your toe hurts right before you have a heart attack too.
Toe starts hurting. Go to the
Yes. So.
doctor. Could have a heart attack.
All right. Now, I use this to bridge the gap because diamond is not ionic, right? First of all, we said what element makes up diamonds? Carbon, right? And carbon is a non-metal, so it can't be ionic bonding, right? So what is going on here? Diamond is the exception when we're talking about molecular compounds. So let's talk more about molecular compounds in general. First, molecular compounds are compounds held together by what kind of bonds? Covalent bonds. And that means they're going to have what kind of elements in them? Non-metals, right? Generally speaking, molecular compounds have lower melting points than ionic compounds, right? Diamond notwithstanding, okay? Because intermolecular forces aren't as strong as interionic forces. What would be an intermolecular force? Not example. What would be the definition of an intermolecular force? Well, what does inter mean? Between, and molecular means molecules, so it's a force between molecules, right? So, covalent compounds or molecular compounds cannot conduct electricity as a solid, a liquid, or when they are dissolved, right? That's a big difference from ionic compounds. Ionic compounds don't conduct electricity when they're solid, but if we melt them or if we put them dissolved in water, they will conduct electricity, right? So, let's talk about why. First, let's review nonpolar covalent bonds. What determines whether a bond is ionic polar covalence or non-polar covalence? Let's go back into the memory banks for this one. It's one word. It's a long word. What's it? What is it? Electronegativity, right? And electronegativity is the attraction of atoms for electrons, right? When we describe a bond as non-polar covalent, what's true about the electronegativity of the atoms involved? I know, it's like, oh, I gotta remember stuff from like Tuesday. So, non-polar. Eric, go ahead.
The difference is less than what kind?
So their electronegativities are very close to one another, right? Different than 0 to 0.4, right? So, atoms have a similar attraction for electrons. So our shared pair of electrons is nice and evenly distributed. And that means that there's no sides that are quote-unquote positive, no sides that are quote-unquote negative. That'll become important here in a second. Okay? We refer to that as nonpolar covalent bonds. Let's write down letters B and letters C, and then we'll talk about where we're going. Okay. So this is nonpolar. Write down this part here. We'll talk about it in a second. Okay. Good with nonpolar? Do we have it yet? All right. Next. Or not. Okay. Polar covalent bonds next. Okay. So, polar covalent bonds. Some atoms have greater attraction for electrons than other atoms do due to their greater electronegativity. And when these atoms form a covalent bond, those electrons will not be shared evenly. We call this a polar covalent bond. Okay, got that stuff written down? All right. So in my hand, left hand, 2 pieces of wood. Right hand, 2 magnets. Okay? They're both solids, right? But there's definitely a difference between a piece of wood and a magnet. Okay? First, let's talk about difference between them individually. Okay? Is there any difference between the left-hand side of this piece of wood and the right-hand side of this piece of wood? Pretty uniform, right? Okay? But is there a difference between the 2 sides of this magnet? Absolutely, right? So, this piece of wood is representing what kind of a bond? Nonpolar or polar? Nonpolar. Nice even distribution, nothing different from anything else. Here, though, right, that's representing our polar bond, right? One side of this magnet is different from the other side of the magnet. Just like in the polar bond, right, we have the one side of the bond being kind of positive and the other side being kind of negative. That sound familiar from the other day? Okay. So, right, that leads to this happening, right? Hopefully, just hold on. Not quite. A little too heavy, right? You get the gist though, yes, right? That the north and south pole of one magnet attract the north and south pole of the other magnet. Yes, even though I have to hold it in the middle because it's too heavy, right? But, right? Is there any attraction here? No, right? Which one's easier to separate? The wood as opposed to this, right? Greater attraction here, less attraction here. Does that make sense? Okay? So, this attraction between these 2 magnets represents something that we refer to as a dipole force. Okay? Notice the picture down on the bottom right of your outline. Okay? That little eggy shape represents a polar molecule. Okay? I would actually probably modify that picture just a little bit. What could we do to modify that picture to make it more representative of a polar molecule? Any ideas? So, what are the 2 different sides labeled as? of each, what are the two different sides of each egg labeled as? Positive and negative. But is that actually the case in a polar molecule? We could do the little fancy sign, right? The little lowercase delta, right? Or what could we do to sort of represent that nature of that it's not exactly negative, but it's negative? Right? Remember we talked about the quotation marks, right? So, and those little blue eggs, yours are gray, but, right? Maybe in front of that positive and negative, instead of just having it straight up being positive and negative, maybe we add that lowercase delta. Or maybe put quotation marks around our plus or our minus to remind us that there really isn't a cation and an anion there. It's just sort of a separation within that same substance. Okay? Does that make sense? But when you see how they're all arranged in relation to each other, what do you see? How are they matching themselves up? How are they twisting and turning in relation to each other? Go ahead, Charlie. Positives are getting close to negatives, and negatives are getting close to positives, right? And that causes them, those molecules, to do what to each other? They're attracting each other. Are they attracting each other as strongly as this? Because this is positive and negative, right? Cation, anion. Totally positive, totally negative. But there, those two sides are what? Meh, right? Kinda, right? So, a dipole force is when the negative end of one molecule is attracted to the positive end, right, quotation marks, of another molecule. A force between dipoles, right? Do we get the origin of dipole? Right? Di meaning two, right? And we've already talked about pole, and polar means what? Separation, right? Okay. These aren't as strong as interionic forces, but they're stronger than the very, very weak forces that barely exist between non-polar molecules, right? It's the difference between the magnets and the blocks of wood, right? I guess using these magnets is even actually a better description of the dipole, because they kind of hold each other together, but not exactly, right? Does that make sense? Okay. That being said, differences between polar and non-polar covalent compounds or molecular compounds. Polar molecules will attract each other slightly, whereas non-polar molecules have virtually no attraction for each other. Polar compounds have slightly higher melting points, but they are nowhere near as high as ionic compounds. Neither has the ability to conduct electricity, and polar compounds will dissolve other polar compounds, but not non-polar compounds. Okay? Good there? Okay, so the differences between polar and non-polar compounds are illustrated by this. Okay? So, here's hand sanitizer. Okay? I still refer to this, and in my house we refer to this as quick wash, because when my kids were growing up, like, we said, hey, just go quick wash your hands. You know, so this is quick wash at our house. But, it's squirt it into your hand, right? Rub it for 5 seconds. What happens? Well, germs come off, but what else comes off? The wetness, right? What is this hand sanitizer made out of? Do we know?
Alcohol.
Alcohol, right? So, active ingredient, ethyl alcohol, 63%. Okay? How much does it take to evaporate the ethyl alcohol in this hand sanitizer? Well, 63% is how much it percentage it is, right? Well, how much does it take to evaporate this ethyl alcohol? Not a whole lot, right? All you got to do is what? Rub your hands together, okay? The energy that you are supplying by the friction or the heat that's being created by the friction is enough to evaporate this ethyl alcohol. Can you get water to dry off of your hands by rubbing them together as well? Takes a lot longer, right? So what does that suggest about ethyl alcohol versus water? It's which melting point of what is lower? Alcohol. Except in this case, are we talking about melting point? We're actually talking about what? Evaporation point, right? Because it's turning from a liquid to a gas. We could say it's the boiling point, right? Did you say boiling point? Evaporation point, yeah, right? But we're talking about turning it from a liquid into a gas. Hey. So, the evaporation point of alcohol is lower than the evaporation point of water. Okay? That being said, which one has greater forces of attraction? Water. Harder to turn from a liquid into a gas. Okay? That means that water is more polar than alcohol is. Does that make sense? Okay? All right. Last thing. Oh, sorry. Bottom of the previous page. Bottom of the previous page. You have a picture of these water molecules right here. Okay? Water, if you look, anybody have their notes from Tuesday out on electronegativity? Just have it handy like on your desk. Yeah, okay. So, water, we know, is two bonds, right? One between oxygen and hydrogen, and then one between that same oxygen and a different hydrogen. Okay? Electronegativity of oxygen. Flip it to the front. So, electronegativity of oxygen is 3.5. But the electronegativity of hydrogen is 2.1. Do some subtraction. What's the difference? 1.4, right? Yes. Okay. So, 1.4 is the difference in electronegativity. Which one wants the electrons more? Oxygen. A lot more. Right? It's not an ionic bond, because what's the cutoff for ionic bond? Those of you that have your outline out. Flip it over to the back side. What's the difference? What's the cutoff for the difference of the ionic bond? 1.7. It's pretty close though, right? Water is a highly polar molecule. It's a very strong magnet with differences between the negative side, quote unquote, and the positive side, quote unquote. Okay? And you can see that in this picture, right? The two little Mickey Mouse ears are your hydrogens. Right? They're the white ones in this picture. Okay? The red one is the oxygen. Okay? Notice how they're lining up though. Right? The oxygen side flips itself around so that it's facing towards the positive. The oxygen side is the quote-unquote negative side, right? Flips itself around so that it's facing towards the quote-unquote positive side of the other water molecules, right? Good there? Right. So, let's talk about oxygen and why it's weird. Okay? Know what this is? Water, yes, but this is ice. Okay? So, here's ice. Is it water? Yeah. And if you look on the edges, right? Here's a red oxygen, here's two white hydrogens. But then when you look through the rest of it, what do you see about how they're arranged? They're very tight, okay? But what order do they go in? Red, white, red, white, red, white, red, white, okay? Interconnected, sure, right? It's not like the graphite that's in rows. Lots of interconnection here, okay? But one thing that makes ice do what it does is this. Okay? So, what is there in between all of these water molecules? A bunch of space, right? And what does that do to the density of this ice cube? It's not very dense, or at least it's not as dense as diamond, true. What else is it not as dense as? Regular water, or water in what state of matter? Liquid, right? The polar nature of water allows it to arrange itself like this, so you get a bunch of spaces in there and it makes the density really low. But when it's a liquid, these things can twist and turn and kind of move, and they actually get closer to each other. Water is one of the weird things, one of the only things out there that is less dense as a solid than it is as a liquid. And it has to do with the polar nature of water. Okay? Good there? All right. So, last thing. This, okay? I should probably show it on the camera, but okay. This is carbon dioxide. I think most of you probably know carbon dioxide is what state of matter? Gas, right? Okay. Carbon dioxide is a non-polar molecule. All of these combinations, 1 black, 2 red, CO2, right? Even though there are these lines between them, because we have to have that, they are not really affecting one another. They're a bunch of wood blocks that just sort of go about their business, right? And as a result, it's nice and easy to make it a gas because they don't hold on to each other. David, go ahead.
Is it possible to have like some sort of gas where the individual atoms actually oppose each other?
Yeah, in this, right, in water, we can turn this into a gas. Gases are chaotic in that the particles move very fast and they're kind of far apart from each other, but they do run into each other all the time. So this lines itself up in this way because positives and negatives are trying to get near each other, right? But in a gas, if these things are moving real fast and flipping and turning, it's possible that as two water molecules, steam molecules, gaseous water, right? When they come to each other, if the oxygen and oxygen side were heading towards each other, they would just repel each other that way, right? Things that repel each other actually would make good gases because they don't want to be together, right? Things that have attractive force for one another are solids. If they're repelling each other, that would make a good gas. Okay. All right, good there? All right, don't worry about the hydrogen bonding side on the back page. We will kind of skip over that. That's advanced sort of stuff anyway. Okay. All right, so Monday, get your safety sheet signed. Watch the awesome Bunsen burner videos. I'll put them on the website. So okay. And we'll talk about lighting fires on Monday. Yeah. Woo.
Just like stop. Yeah, I was.